Myself, Dr. K. Rajendra Prasad. I am working as professor and head for the Department of Cyber Security. Today, my topic is some part of the structure of compiler. So, in the structure of compiler, already we have to see in previous lecture totally for 7 number of phases. So, which are comprised into totally for 2 different parts: analysis part and also synthesis part. In the analysis part, we have to done totally for 4 things. That comes lexical analyzer, syntax analyzer, semantic analyzer, and also intermediate code generation. In synthesis part, that can be framed with totally for 2 phases, which are called as code optimization and code generation. So the discussion is completed in the earlier class. Today we are going to discuss about finite automata. Because of in the lexical analyzer, I think we have some important concept, that is recognizing the tokens. So using input buffer and using the total for 2 pointers. Already we have discussed earlier. Therefore, 2 pointers. How can we separate the tokens and how can we recognize the tokens with the parsing mechanism? So that can be actually implemented by some kind of ideal mission. This is called as finite automata. So that's right. Today we are discussing about finite automata. Finite automata is a simple idealized mission used to recognize patterns with the input taken from some character set. Nothing but here, whatever characters you have to provide in the source programming language statements, you have to read each character at a time by the head of the finite automata. Means at each time the head is scans or the head is moves from left position to right position. With the help of that, it reads a single character at a time. So this finite automata that can be used for recognizing the tokens. Recognizing the tokens is the important idea of lexical analyzer. Therefore, at the time of compiler construction, especially in the first phase of lexical analyzer, we are using the finite automata. Finite automata are useful for compiler construction. Not only for the compiler construction, it can be also used for some ideas of theory of computation and artificial intelligence and also parsing and formal verification. But majorly, we are discussing in the compiler construction. In the compiler construction, finite automata are very useful. So we have to see what is exactly finite automata. What is the definition of the finite automata? So finite automata are recognizers because of we are recognizing the tokens or we are recognizing the lexemes using one kind of ideal mission that is called as finite automata. Therefore, finite automata that can be used for recognizing the tokens in the lexical analysis part. So simply after recognition, simply have to say that 2 Boolean answers. Whether the string is accepted, then you call as yes. Whether the string is not accepted, you call as no. So this is the output you have to guessing from the finite automata. Means after construction of the finite automata, we have to receive the total for the outputs are whether the string is accepted. That case, the output is yes. The string is not accepted by the finite automata. This called as a no. Because of every language, okay, not only for the C and the C++, you are taking the any language in the real world. Language nothing but basically you have to follow some grammatical rules and syntaxes and as well as some special constructs. In the language, you have to recognize only for the language words only, language tokens only. In that case, initially you have to use or you have to construct some different finite automatas for recognizing each and every syntax so that with the help of the finite automata, it is easy to construct the compiler construction. So with the help of the finite automata only, you can recognize the language strings. In that case, automatas are very useful. So we have to, there is some relationship between the finite automata and the compiler construction because of in the first phase of the compiler construction, it is required to collect the tokens, but it is not possible in a simplest way. So recognizing the token is very difficult and very crucial part that can be implemented by the finite automatas only. Therefore, you must learn the finite automata for what purpose? Nothing but for our compiler construction. Means you want to design any new programming language, that case, it is required to design new compiler also. So for the compiler construction, you must remember the prerequisite information is finite automata. So now we discuss about the finite automata definition. So actually the finite automata that can be visualized with the 5 tuple syntax. Or tuple is also called as a variable, is also called as a 5 variable syntax. So we have to discuss what the 5 variables are. These are the 5 variables. Here I'm writing these are the 5 variables. Capital Q, sigma, delta, Q naught, and capital F. So what is each and every tuple and each and every variable nothing but, so all 5 variables are very important for the automata construction. So you must aware all these 5 variables. So entirely this is called as the definition of the finite automata. Means we define the finite automata with the help of the states, that's called as the capital Q, and with the help of the transition symbols, that can be derived from the input alphabet only, that's called as sigma. After that, so we have to deciding finally we are reaching to what state and how you are reaching using what is the current state and what is the current symbol. So that idea is called as some transition function is delta. I will tell you later. So what is the delta is completely. What the idea of delta. So I will tell you in the coming slide with the example also. And the next one is the initial state. Q0 is the initial state. Means we have defined many number of states in the finite automata, but all are not initial state. Only one state that can be considered as the initial state. And one more condition in the finite automata is they must be defined only for single state only. Means you have to start it from which state. Suppose I am taking for 3 different states Q0, Q1, Q2. Among these 3, only for one becomes only for the initial state only. So initial state nothing but how many number of initial states? Exactly one. For any kind of finite automata problem, you are taking the only for single initial state only. Next, we have to come to the set of finite states. What are the set of finite states, sir? So you have to ending with some number of states. Means where you ended or where the machine is terminated, at what states, those are called as final state. There is possibility we have to getting either one final state or more than one final states also. But in the case of initial state, you should allow only for exactly for one single state only. This is the brief idea regarding to the definition of finite automata. So we have to see that what are the types of finite automata. Non-deterministic finite automata is one type, one particular type is we are using currently, and one more is deterministic finite automata. There is a lot of difference between these two types of machines from characteristic point of view. So what are the two characteristics where these two are different is mainly is the two important characteristics we are defined now. So only for one category of mission that satisfy these characteristics, remaining other is cannot satisfy. What are these two important characteristics? So we have to take an suppose one state here. Define the state with some circles only. I am taking here. The state is started from Q0 and ending with Q1. So you must remember before going to discuss these two types of finite automata, you must know some prior information. So one is regarding the initial state. Initial state. The initial state that can be defined, the symbol is arrow. That can be defined as arrow. One more is final state. The final state that can be defined with two circles. That can be defined with the two circles. Suppose here I am taking the diagram is one more. I am taking one more diagram. I am taking the diagram is like this. Suppose you take one real-time example. One student is there. He started from home. H nothing but home. We are assuming H is a home. And he started from the home. He may be traveled by bus. He may be traveled by the bus. And reaching to another state is college. Another state is college. So after the college, again he may return to the home. He may return to home by the same bus. So we have to see this structure by one finite automata. Here, what is the starting is, so where the student is started every day is from the home itself only. That's why here I define the starting symbol is capital H, starting state is capital H, defined with the some arrow mark. Here you can define where the arrow is defined is at H only. Therefore, H is considered the some initial state. Which is considered the some initial state. Okay, and one more thing is we have defined some transitions. The transitions are called as H to HC. C nothing but home to by travel is bus only, and he reached to the college. Again, after the completion of the college, that on that particular day, again by the bus, again he may attempt a return journey. Again, he reached to the home only. So finally, it started and ending with the same state. Again, here H is also called as ending. So means in that particular day, what is the activity of the student is where he started again, reached to the same place. Means started from the home after college again. He may not be stay at college. Again, he returned to home. So again, the process is completed. So that's why here also you have to put the double circle. So because of H is the ending state, or it is also called as the final state. It is also called as the final state. So ending or final state that can be defined by what kind of symbol is a double circle. Double circle. So we have to define totally two types of symbols for defining which is the initial state and which are the final states. That purpose, I am taking the two different symbols. So I do nothing but this called as starting state defines the starting state. This called as starting state, and double cycle that can be defined. The purpose is final state. Final state. We should remember these two different symbols for defining of the purpose is the starting as well as the final states. So we have discussion is so what are the types of finite automata, and describing a finite automata. The sample example is, I think you got some idea regarding the set of states. Here I am taking the set of states. Capital Q is what are states, sir? H comma C. And what the sigma is? So means what are the transition symbols? On the transition we use what symbol is bus. Okay. Here this transition also bus. This transition also bus. This transition also bus. And after that delta, I will explain what the delta is later. And next one is what the state Q naught, initial state. Here initial state is H. And what is the final state is? The final state is F is also H. Means you can describing the set of states are H comma C, and the sigma is transitions, and transition what symbols you are using is a bus symbol only, and come to the what is the where you started is from H only the student is started, and again ending with the same H only. So capital F is H. So this is regard to the five tuple syntax. Now we are discussing what is the non-deterministic, what is the deterministic is. Coming slide, I will explain what is the idea of non-deterministic finite automata. Here the idea is very simple. Suppose any finite automata diagram, it allows null symbols. Sometimes the transitions may have the null symbols also. Null symbol is appeared in the diagram. Then blindly you can say that that comes under the NFA, non-deterministic finite automata. Means the first character is in NFA. Suppose finite automata allows null symbol that can be defined with epsilon. Epsilon defines the null symbol. It's called as null symbol. So that's the first criteria. So the diagram having any null transitions, like example is suppose you are taking the state is Q0 and you have to reach to Q1. Therefore, the null transition, the symbol is null transition. Here, this transition is called as a null transition. This transition is called as a null transition. But then that kind of mission is this mission is NFA. Because of this tag, we have the null symbols. Suppose I am taking another diagram for differentiating. For what case you cannot say the diagram is null in if a diagram is. So I am showing you one more best example is here. I am taking two different states. Final state is Q1 and initial state is Q0. So here, how many number of final states are? Double cycles are defined in two cases, Q1 and Q2. These are the final states. Totally, I am defining the two different final states. So what the initial state is? Initial state is Q0 only. So here I am defining the labels are small a and small b. You can verify that clearly. Here there is no transitions. There is no null transitions. No null transitions. I am writing here no null transitions. So in this diagram, no null transitions. So this diagram excludes the null value at any transition. So only we have defined two transitions only. One transition symbol is a small a, another transition symbol is a small b. Therefore, this diagram cannot have any null transitions. This kind of diagrams are called as it may be BFA diagram. So not only for this simple condition, we can also verify the another condition is. So another condition of the first condition is NF nothing but it may have the null transitions. Suppose any diagram have the I'm writing null is with the symbol of epsilon. You are recognizing any transition with the null move, that transition is called as a null transition. That is also called as an NFA diagram. One more case is, it is a very important case. So you are reaching to more than one distinct states. Means the number of output states are more than one from the same source of state and same input symbol. Means the idea is here I am saying Q0 is one of the source state because you should started from the source state is Q0 in the same state, the same symbol. Okay, what do you mean is here I am taking the state Q0 and also here. So here I am writing delta of Q0 and here like this. That's the idea of delta. Means the delta is nothing but it takes the two input values. One input is state, one input is the transition symbol. It is a state, it is a transition symbol. And after that, again I want to draw another transition. It also with the same symbol. It also with the same symbol here. So here you can observe that but two different states reaching to two different states. Means the meaning is delta of Q0 comma A result is one result is delta of, you can apply this result, then the output is here Q2. So you have to go for Q0 and A. Another case is the output is Q3. So means here you may have some kind of ambiguity because of I am using the source is same. Source state is Q0 and symbol is small a. But one case is we are reaching that the thing is Q2 state. And another case is the same source information, the same input symbol. That is, I'm using same state and the same input transition, using the same input transition, but we are getting a different output states. What happens is there are more than one output states. For the same state and same source state and same input transition symbol. Then that kind of machine is called as non-deterministic finite automata. It's called as non-deterministic finite automata. Means here defining the total for two cases. What cases you are assuming the non-deterministic finite automata is it may allow the null transitions, and one more thing is it may have more than one output states for the same source state and same input symbol. Then that idea is called as non-deterministic finite automata. So this non-deterministic finite automata also defined with total the same kind of finite automata syntax. Here also we follow the phi tuple syntax. So these phi tuples are same. You observe it. In the diagram, what are the set of states? That's called as capital S. In the diagram, for the transitions, we are using what are the different symbols. Those symbols are called as input alphabet. And third one is based upon the one current state and the current symbol, you are reaching to what is the output state. Means here you try to defining some kind of a transition function that is called as delta. That is called as delta. So delta is nothing but it may have the result is sometimes null, or it may have the result is more than one states. So that's why you can also include the delta is nothing but it includes the null value also. This is the idea of delta itself. And the fourth one is where you started, to what state you are considered as a starting state. In the diagram, n number of states are there. Only for one particular state it becomes the starting state. That is, you are assuming the S naught. Or in our previous slide, you are assuming the Q naught. And a set of states, some subset of the states, okay, it may have the final states. Because of in the diagram, we should remember always one condition is the initial state is only for single initial state, but come to the final states point of view, more than one final states you are assuming. So that's why, so the F nothing but it may be have the some subset of states. So those final states are also called as accepted states. So this is the definition. And what are the conditions of it may have the null transitions. One more condition is we have to reaching more than one distinct output states using the same input state and same input symbol. So that is the basic idea of non-deterministic finite automata. Because of we are using sometimes non-deterministic finite automata, sometimes we are using the deterministic finite automata in for the case of compilers construction. So that's why we should remember so both types of machines, NFA and as well as DFA. So here I am giving the one more better example of non-deterministic finite automata. Here my question is why it is considered as a non-deterministic finite automata. So we have to see the one particular case is the case is the state is here 0, the current state is 0, yes, and the current symbol is you are taking, I am assuming the current symbol. The current symbol is becomes here. So we have to define delta of 0, here is a state, is the transition symbol, So using 0, a, so one is I'm putting the tick is a combination of 0, a. It goes to again 0. The output is 0. So another case is using 0 and a. So we have to consider this as this two or the state is 1. So finally, you are reaching more than one different output states. For the case of the source state is 0 and transition symbol is a. So one possibility is reaching to the same state, one more possibility is reaching to 1. So finally, what are the output states you are considering? But either 0 state or 1 state for the symbol of the same symbol is a. So hence this one is NFA. Here also one final state defined. So here how to recognize the final state is you can identify that where is the double circle notation. Here in the 3 is double circle notation is there, so it is called as a final state. The final state is only for the 3. So what the initial state is? The starting state, arrow mark, arrow it indicates the initial state, it becomes 0. So there is one well-known example of non-deterministic finite automata. So we have to defining one more extended idea is the non-deterministic finite automata is for finding the delta. Because of in the 5 tuple syntax, 4 tuples are easy to understanding. What the tuples are? Q, set of states. What is set of states in the diagram is 0, 1, 2, 3, 4 states are defined. And sigma is this is an input alphabet, means on the transitions what are the symbols you are using. On the transition you are defining what the symbols are, different symbols are only for 2 symbols only. Small a, small b is called as a sigma. After that we define the delta. So delta we can say in a single line or single word. Delta that can be added is the transition function. So transition function, but as per the functions concept, the idea is, I think it may be have the form. This is the input, this for the output. That is idea is the transition function. So what the input is? The input you are taking totally for two values. One is the state, one more is the transition symbol. One more is the transition symbol. So here I am taking the state. Okay, these are the transition symbols. Here I am including the null symbol also because of here we are getting the problem is the null transition. So that's why this table is also called as delta. Delta is defined with the transition mapping function or transition mapping function values that can be defined in terms of a transition table. So this is the transition table for this transition table that can be obtained from this mission only. You check one example is 0, you are taking the current state. Using A is we have the two cases. One is using A reach to 0. One more is using A. You can check this case is reaching to 1. Similarly, 0 using B. Here 0 using B is self loop again reach to the same state 0. Like that, once you know the finite automata, from that you can finding the output states. Therefore, the transition function is very easy. You want to define all values of the transition function. That the better notation is you are taking a transition table. Now, this kind of table is called as transition table. Means after applying the delta on given finite automata, you are getting some table values. That values are called as a transition table. So similarly, after getting the transition table, suppose you want to verify with a finite automata, with a non-definite finite automata, whether the language string is recognized or not, language string is accepted or not. You can verify that 3 A's, 1 is 2 B's. So my question is whether this string is accepted or not. If applying the delta for the starting state, you are taking the 0, 3 A's and 2 B's, you can solve this problem. So finally, you have to reaching the final state, then the string is accepted. Now I am showing that the delta of 0, A, you may have attend again 0, you may reach the 0, 2 A's and 2 B's. Again, you may reach the delta of 0, A. Next time is you are applying 0, A is 0 and A. You are getting the result is 1. Delta of 0, delta of 1, B. 1, B nothing but delta of again 2, B. 2, B is nothing but finally 3. 3 belongs to final state. Means the final state is the last obtained state is the final state. Then this string is accepted. Otherwise, the string is not accepted. Now you have to conclude that 3 A's 2 B's is accepted or is recognized as the language string by NFA. Because the reason is finally you are reaching the final state. You are reaching the final state or accepted state. Means when solving the problem, therefore the delta function, the last state is the final state. The last state is the final state. Okay, then the string is accepted. It is a way for showing the steps of acceptance of some input string is 3 A's and 2 B's. So like that, we should exercise for any other relevant example also. Next case is deterministic finite automata. Once you are understanding of NFA, then DF understanding is very easy. Means in the NFA, you should allow the null transitions, but in the DFA, you cannot allow the null transitions. This is one important condition. One more condition is in the NFA, there is possible to get more than one output states using the same input state and the same transition symbol. But here, there is no such possibility. The number of output and number of reaching states are strictly only for one only. So it means the number of output states are not either 2 or more than, I think, using the same source state and the same transition symbol. Means it allows strictly single output state only from the same source state and the same input symbol. It totally reverse of the NFA. In the NFA, you should allow the null transitions, but in the DFA, you cannot allow the null transitions. One difference is there. Another difference is in the NFA, there is possibility to get more than one output states also when you are applying the same source state and same input symbol. But here, we are getting the number of reaching states and number of output states are strictly for one using the same source state and the same input symbol. So this is the characteristic of DFA. And as per the definition, okay, you should follow the same 5 tuple syntax. But only the difference is you are wearing the delta function only. In the delta, previously you are taking the some q cross sigma 2 sigma star 2 q star nothing but it may include the null value also, where in the case of NFA. But in the case of DFA, the transition function is q plus sigma 2 q only. Means the sigma is any input symbol. You cannot allow the null transitions. And some of the times you may getting the states are here 2 power q form, but here exactly for the q only. Output state is only for single state only. So only the delta is different when you comparing the syntax of NFA and DFA. Remaining 4 variables are common. Q, sigma, and starting state, final states, these are common. Only delta is different. You should remember delta of NFA is q plus sigma star 2 power q. Why I am taking the 2 power q? Nothing but any subset you have to getting. Subset nothing but more than one states you have to getting as output. But here you are getting not in the subset form. You are getting only for the single state only. So this is the DFA syntax and DFA delta function is the q cross sigma 2 q only. And what are the relevant examples? So you are taking any relevant examples, but in that case you cannot take the null transitions. So here I am taking one example is like this. Here A, here B. You check that here the symbols are different. No null transitions. It is called as DFA. Suppose I am taking here the symbol is A, then it is not a DFA. It is not a DFA. It is not a DFA. It is called as a NFA, because the same symbol you reaching the two different states. So it is called as a DFA. One more example is suppose I am taking Q0 to Q1. Here I am taking null transition. It is not a DFA. It is not a DFA. Suppose there is no null transition. There is no null transition. We have the symbol. Then it is called as a DFA. So there is, I think the difference is very clear. No null transitions in the DFA. Strictly, it allows only for single output state use the same source state and the same transition symbol. So this is the idea of DFA. So I have referred the concepts of finite automata and the types of finite automata and relevant examples and exercises. All are I am getting from these two references. Once again, thank you for all.
Like, share and subscribe. Hit the bell icon for more updates.